All right, I want to thank everybody coming out tonight. I see a lot of new faces at our monthly talks, which is great to see. This is as long as I've been in the organization, this is the first time we've had a talk at BU for as long as I've been here. And this is really exciting to see the turnout we've gotten on our first day, our first time here. So I want to thank Thierry and Vanita for helping to organize this with me. I wouldn't have been able to get this space without them, so they were very helpful and gracious for being able to coordinate with us. We are planning to have more here in the future, so keep an eye out. This will not be the last time that we're at BU. We'll talk a little bit about Daniel. We met for the first time in person. We had a social in April at Aeronaut, and I pitched to everyone at this event that if you wanted to give a practice defense or practice, talk for your defense, because we had a lot of students in the audience, reach out and we can arrange it. And so Daniel took the initiative and actually did, and he reached out and wanted to give a practice defense talk, and here he is. He's getting ready to defend. I mean, that's an achievement in itself, because I know how tough it is to get there. So I'm going to hand the floor off to Daniel here, who's going to be talking about high-dimensional optical orbital angular momentum entanglement in optical fibers. And he's going to be giving this as his defense talk here. Thank you very much.
All right. Thank you very much, Sanjay, for this very nice introduction. And I would also like to thank NES Optica for organizing this event and giving me this opportunity to present on my defense. So, and of course, thank you all for joining me today. As you can see from the title, this talk, the ultimate goal for this project is going to be on high-dimensional orbital angular momentum entanglement in optical fibers. However, the focal point of this talk is going to be more specifically about the physics and the properties of the fiber platform that we use as a prerequisite to achieve such entanglement. So the following is the outline of this talk today. First, I hope to motivate the topic a little bit more, why we care about high-dimensional entanglement, why use OEM modes, as well as why do so in optical fibers. Then I'll go ahead and introduce our fiber platform, which is going to be the ring core fiber, as well as its constituent OEM modes, as well as their properties. Then I'm going to lay some basic ground rules for intermodal spontaneous four-wave mixing, which is going to be the process which we use to generate single-photon pairs. And the second part of the talk, I'm going to present some experimental results. And then finally, I'm going to outline some future steps of where this project is heading. So as many of you probably know, there's this huge push today that's referred to as the quantum 2.0 revolution, which promises quantum technologies that achieve supremacy over classical ways of doing things today, such as faster computation, more secure communications, more precise metrology, and so on. But the backbone of all of these quantum technologies has been these two-dimensional quantum states, which are known as qubits, that are essentially can be written as a superposition of two basis vectors labeled as 0 and 1. With two particles, you can have more exotic states, such as over here. This is a maximally entangled state, which essentially just means that you cannot write it as a separable product state of one state for each particle. And this entanglement is really, it lies at the heart of many of the quantum technologies today. When it comes to physical implementation, and especially for photons, the most natural degree of freedom to pick is the photon polarization, because it is inherently two-dimensional. However, we're not necessarily restricted to up to two particles or even up to 2 dimensions. You can increase your system complexity by introducing additional particles. Those are known as multipartite state, or you can increase the dimensionality of your states. And of course, when you do so, you can expect to unlock new technical capabilities. And so for our perspective, we're going to look at a photon pair, so only two particles, but exist in a high-dimensional space, and so we call them qubits. And so this is a general representation of a maximally entangled d-dimensional state. So these high-dimensional states are advantageous over two-dimensional ones for a variety of reasons. For example, one, they carry more information capacity per photons. They offer better channel security for QKD applications, and they also exhibit greater violations of local reality, which is the essential property of entanglement. So while polarization no longer is sufficient to encode information because of its two-dimensional nature, the question now becomes, which other degree of freedom of light can we use to encode information? So there are a variety of options to pick from. Each of them has its own pros and cons. So for example, we can encode information in discrete time bins, which is fairly easy to create because it can just pump a nonlinear crystal with a pulse train, and then you have your state. But then the problem becomes when you want to mix between these time bins, you're going to need to employ some cascaded friends and interferometers, which becomes a lot more complex as you increase dimensions. Likewise, it's very easy to encode information in frequency bands. You can just pump a microring resonator to get all your comb lines. But again, in order to mix between those frequencies, you're going to need to have electro-optic modulators that are lossy, but also have non-uniform modulation amplitudes. You can encode information in different paths of photons, which is a pretty solid way of doing so, especially in photonic chips. But you're going to need to create de-indistinguishable sources, which becomes more complex as you increase dimensionality, and also the physical footprint increases as you want to add more dimensions. And finally, as something that's a bit more spatially efficient, we can encode information in transverse modes of photons. And so in particular, the most common way to do so is using the free space OEM modes and creating them using second order nonlinear crystals. But because these are free space modes and not fiber modes, it becomes a lot more difficult to integrate them in a potential future fiber network. And also these modes are emitted with unequal amplitudes. And so you have to employ some kind of filtering to equalize these amplitudes, which is very lossy. And so the question now becomes, okay, can we potentially achieve some kind of like entanglement in OEM using fiber modes? So to generate single photon pairs within optical fibers can be done using a process called spontaneous four-row mixing, in which two pump photons are annihilated to create a pair of signal and idler photons that has to satisfy your typical energy conservation rule as well as your phase matching condition. Now, doing so in fiber has some advantages. So for example, this process involves the destruction of two pump photons instead of one. And so that allows you to have more engineering capabilities by breaking the degeneracy of the two pump photons. And also you're generating your signal and idler photons within fiber modes. And so that's going to be a lot easier to potentially integrate it in a fiber network system. So different fiber platforms to create photon pairs already exist, listed over here. But if the objective is to increase the quantum state dimensionality in transverse modes, you're going to need to go to multimode fibers. So the few mode fiber has been shown to achieve spontaneous four-way mixing between different transverse modes. So for example, between the fundamental mode and the high order LP11 even and odd modes. But the problem with this fiber is that the dimensionality is inherently very limited because this fiber can support only so few modes, hence the name. So the natural remedy to that is by going to a highly multimoded fiber, which can contain a lot of modes. But the problem with those is that the modes exhibit a lot of unstable mode mixing, and so essentially it renders it impractical for our source. However, it has been shown that if you go to a multimode fiber that features a reinforced structure to mainly suppress high-order radial order modes, then what you end up with is the stable guidance of high-order OEM modes. So this is the mathematical representation of a typical OEM mode. It has a intensity radial distribution, so it just looks like a ring. It has a helical phase front that is attributable to the OEM of the mode. And this mode also propagates with a certain propagation constant of beta L, which is very important for the purposes of phase matching. So this is an example of a ring core fiber that we use in our experiments. It is a 60 micron core size ring core fiber, and it has been shown to achieve kilometer scale transport of 50 modes at 1550 if we take into account polarization. So now if you take this fiber structure and you solve for all the effective indices versus wavelength profiles for each of the modes, you get this following plot. This plot is pretty important because it encapsulates all these scalar dispersion properties of the fiber, including material dispersion, waveguide dispersion, and more importantly, modal dispersion. And so if you look at this plot and you ask yourself, okay, which modes do we actually have available in our fiber? Well, we have all the modes with effective indices above the cladding index. Those are known as bound modes, and they're guided using traditional total and tonal reflection. And modes with effective indices below the cladding index are cutoff modes, and those would get lost. However, with OEM modes, it actually is not the case. It turns out that you can actually go deep within the cutoff regime to still have stable guidance of OEM modes. And that has, in terms of implications, that just means that it greatly expands our modal range. And so, of course, that brings up the question, why that is the case? How come we can still have guidance of modes despite being cut off? And the best way to answer that is to look at the governing equation for the mode, which is shown over here. And this is essentially the wave equation that solves, for the scalar properties. So over here we have the intensity distribution. It is the eigenfunction of this equation, and then we have the propagation constant, which is the eigenvalue of this equation. And this n over here represents the physical refractive index profile. Now, if you have an OEM L, then the OEM mode actually sees a modified refractive index profile shown over here that's modified by this factor. So if you want to compare the two, this is what you get with the black curve representing the physical index profile. But if you come in with, say, like L equals 70 at 1058 nanometers, the blue curve represents what that mode actually sees. And you can see that with the presence of the OEM, there's a trench that's being formed that is attributed to a centrifugal barrier induced by the OEM itself. So despite being in cutoff mode, the mode is still confined because of this barrier. And hence, these modes are known as topologically confined modes. And they have a variety of different properties, but the one that we care about the most is the fact that they just expand the modal range that we can play with. Now, you cannot jack up the OEM order ad infinitum, because as you keep increasing the OEM order, the propagation loss starts to shoot up quite rapidly, because the barrier is no longer strong enough to contain the mode. And so essentially we have a TCM regime up to a certain lossy limit, which depends on your tolerances. And so, for example, for this fiber and the 1058 nanometer, our TCM regime is at, goes from 49 to 77, for example. So this is what's happening at the high end of the OEM regime, at the OEM range. But what's happening at the low end of the OEM range? Can we go all the way down to L equals 0? So what you're seeing over here is a schematic representation of the effective index levels of the fibers as you increase your OEM order. And over here, I'm specifically highlighting the difference between the effective indices, delta F over here. This delta F is very important because it controls how susceptible two modes are going to mix with each other. If the spacing, effective index spacing is too small, then any fiber perturbations is going to have an easier time to mix between those two modes. And the converse is true. If the spacing is large, then you're less susceptible to mode mixing. So while the effective index goes down with mode order, the spacing actually increases with mode order. And so that essentially implies that there should be that high order modes over here should be more stable than low order modes. And indeed, if you look at the mode images, that is indeed the case. These low order modes exhibit some mode mixing, whereas these high order modes are more stable, which is rather counterintuitive because normally you would think that low order modes would be less stable. More stable. So this is actually not the full picture because I have not addressed the polarization of these modes. So you can have a circular polarization, either sigma plus or sigma minus. And when you're coming in with an OEM, you can come in with a positive OEM or a negative OEM. So it turns out that this effective index level is split into two depending on the sign alignment between the OEM and the polarization. So for example, if your OEM and polarization are both plus and plus, or if it's minus and minus, then we call those modes spin orbit aligned. Whereas if they're opposite signs, then we refer to them as spin orbit anti-aligned. And this splitting is due to an effect called spin orbit interaction. And so this essentially implies that within our fiber, we have a polarization maintaining feature despite being circularly symmetric. So when you take that into account and all these stability requirements, here are the OEM ranges for a variety of wavelengths. And you can see that for a shorter wavelength, the fiber is more multimoded, as you would expect. And for a higher wavelength, it is less multimoded. All right, so we have our fiber, we have our modes. Now let's take a look at what we need to do in order to mix between them nonlinearly. So again, I'm showing over here the mathematical representation for a mode. And in order for the four modes to interact with each other, they're going to need to overlap spatially. And that is quantified by this four-field spatial overlap integral. So this integral features a radial component, which quantifies how well the amplitudes overlap, but it also features an azimuthal integral, which is dependent on this delta L. And this delta L is the total OEM mismatch. So if you look at this essentially implies that in addition to your typical energy and linear momentum conservation rule, we also have an orbital angular momentum conservation rule, which says that delta L has to be 0 because otherwise this integral vanishes. And this OEM conservation rule essentially is very important because it establishes very strong OEM correlations between our signal and idler photons, which is a necessary prerequisite for entanglement. So this is an example of a viable forward mixing process in our fiber that satisfies all of these selection rules. It corresponds to the case of pumping the fiber at 1058 nanometers at L equals -70 to produce a signal photon at 1565 nanometer at L equals -38 and an idler photon at 800 nanometers at L equals 102. What you're seeing over here below these mode images is what happens when you pass these modes through a cylindrical lens, which collapses it into a linear distribution with a number of nulls equal to the OEM order. So it's a very useful tool for us to identify which mode we actually are producing. Because if you just look at the ring, that does not tell you which mode you actually have. All right. So I just showed you an example of one viable forward mixing process, but now the question is, okay, what are the tuning capabilities that we have within our fiber in order to explore other processes? So the best way to answer that question is to go back to this effective index versus wavelength profile, which I showed you earlier. Suppose that you pump the fiber at a specific pump wavelength to produce a signal and idler pair at different wavelengths and at different modes. The phase matching condition in this plot essentially implies that the middle point of the pump has to lie on the line connecting the signal and idler. So this is a very geometric interpretation of phase matching conditions in this particular plot. So over here, I'm showing an illustration of a phase match process. But what it can do is it can also break the pump degeneracy by pumping at two modes instead of one, which essentially defines this delta LP factor. This delta LP is the pump modal difference. How different are the two OEMs of the pump? Here's another example of a phase match forward mixing process, and you can even have negatively sloped forward mixing processes. And so in this picture, this essentially implies that if you have a highly multimoded ring core fiber with a very high effective index density, then you have many forward mixing possibilities to explore. It essentially becomes near continuous, even though you're changing discrete numbers, that is the OEM. Excuse me. So here are two different iterations of ring core fibers that we're going to use in these experiments. One is a 30 micron core size ring core fiber, and one is a 60 micron core size. And as you would imagine, in terms of the effective index density that I just referred to, the 30 micron one is a lot less dense than the 60 micron one. So if you want to have a lot of processes available, you would want to go to the highly multimoded one. All right. So that was some background on our fiber platform, as well as its modes and some of its nonlinear mixing. Now I'd like to move on to some experimental results. First, I'm going to discuss about a beam sculpting technique that using MPLC that we use a lot in our lab, and that is very useful to whenever you're dealing with more complex, spatially complex fields. Then we're going to go and show some results for the emission of single photon pairs with OEM, and then we're going to expand the dimensionality by searching for more processes. All right, so because we're dealing with complex spatial modes, we want the ability in our lab to convert, say, like a Gaussian beam to an OEM mode, to say, for example, pump the fiber, and in the reverse process of taking an OEM mode and converting it back to a Gaussian to, say, like process the signal and idler photons that are being emitted. We want to do that for a single OEM mode, but we also want to do that for a general superposition of many OEM modes at once, which have a bit more of a complex structure to them. So the way that we do that in our lab is we employ a double element beam shaping method, which essentially consists of two phase plates that are separated by free space propagation. Now, so suppose you come here with an input field, say typically a Gaussian beam, and you want to convert this Gaussian beam to some complicated target field. What you can do is you can compute the first phase mask such that when you propagate it, the beam evolves to the same amplitude as your target. But this guy is going to have a different phase than your target. So what it can do is it can use the second phase plate to correct for that phase, right? And this setup is ideal because we're only using phase elements and not amplitude elements, and so it is inherently lossless, right? And we compute these phases using an inverse design algorithm called multiplane light conversion. And here's an example of how it works. So say, for example, we're coming in with a Gaussian beam, and we want to convert it to a superposition of L equals 60 and 63, right? When you coherently add up these two modes, your intensity pattern develops this three-lobed feature. So what you do is you initialize your masks. So say, for example, blank masks. You apply the first mask onto your input field, and then you propagate the input field to the second mask, which is still a Gaussian. And then these guys are going to have a different phase profiles. And so what you can do is you can update the second mask to essentially phase match the two. Then with this updated mask, you can apply it to your target field and then propagate your target backwards to the first plate to get a different field. And then these two guys are phase mismatch, but then you can correct for it by updating the first mask. So that's one iteration. And then when you take this mask and then you apply it on the Gaussian, we can already see that within one iteration, it already starts to develop a ring structure with three lobes to it. So when you carry out many iterations, eventually it converges to some phase mask solution. And so for this particular example, the solution converges to something that achieves about like a 96% conversion fidelity. So while this beam shaping technique can be, because this beam shaping technique can be broadly applicable beyond our fiber modes, and instead can be used to generate any kind of complex shape. We tested this method on the Laguerre-Gaussian model basis because that is something that the community is more familiar with rather than our fiber modes, right? So over here I'm showing a select profiles for the Laguerre-Gaussian mode family. From -25 to 25. And if you add them all up coherently, you get this new complicated interference pattern with a certain intensity and phase profile. And this is going to be the target that we want to create. We called this guy the rectangular cone because of the way that we constructed it, right? You just add up all these OEMs with equal weights, and so its OEM spectrum looks like a rectangular spectrum. But to show the versatility of this method, we can try to generate some other complicated shapes like a sinusoidal spectrum, a Gaussian spectrum, or even a sinc spectrum. So with some experimental parameters, you're defining your Gaussian size, your target size, and the plane space in between the two plates. You can run MPLC to obtain your phase mask solution, and you can numerically test them to see how well the algorithm produced, and indeed we obtained phase masks that match the target pretty well with about 99% fidelity. But these are simulations. We want to actually implement them experimentally, so this is a simplified version of the setup. It involves an SLM that's divided into two, which allows us to project two independent phase masks. We have a 1550 nanometer beam that's configured to bounce through both phase plates. And so after this SLM, we essentially have our rectangular comb or any comb that we want to test. And in order to determine what is the power level at each L within the spectrum, we have a second SLM over here. We apply helical projections, and that together with coupling to a single mode fiber allows us to measure the power component at 1L. So to do that, so we did that for the rectangular spectrum, and this is what we get. And we see that it kind of captures the breadth of the spectrum pretty well from -25 to 25. Although with some fluctuations, we quantified the flatness of this spectrum by calculating the relative standard deviation to be about 17%. We also measure the losses of these phase plates by measuring the total loss through this SLM. and subtracting off the material loss of the SLM. So this is the loss attributed specifically to the faceplates. Doing that for the rest of the combs, this is what we get, and we get very similar results, pretty closely matching spectra, especially for the Gaussian and sinc distributions. So this is a tool, a useful tool that we use a lot in our lab. All right, so with that out of the way, there's another very important thing that we need to look at, and that is the what we call the joint spectral amplitude of our photon pair. This function essentially contains all these spectral properties that you need to know about your photon pair, including where it shows up spectrally, whether it has any kind of spectral correlations, and any other features. So in terms of like where we want these processes to show up, we want to choose them such that we can pump our fiber using a 1 micron source because of source availability. And we want our signal photon to show up at 1550, which is ideal for telecom applications. And we want to choose our idler at around 780 nanometers, which is good for, say, like quantum memory systems. In terms of correlations, you can have correlated or anti-correlated JSAs, which are good for frequency entanglement, or you can have uncorrelated JSAs, which is good for a heralded single photon source. The JSA follows this complicated convolution integral, but essentially it can be boiled down to two parts. One is a contribution due to the pump spectrum, and the other one is a contribution due to the phase mismatch between the four modes, right? And so while this JSA is inherently a quantum function, a quantum property, we can actually efficiently measure it using classical methods. So this is a simplified setup of how we would measure it classically for a given process, right? So this process essentially indicates that we're pumping our fiber with L equals 20 and L equals 20, so a degenerate pump, to produce a seed at L equals 17, sorry, a signal at L equals 17, and an idler at L equals 23. So we have our pump over here. It is a 150 femtosecond pump centered at 1038 nanometers with a 10 megahertz rep rate. And we convert it using a single bounce on the SLM to convert to the right mode. We're not using the two-plate MPLC in this case because in this case, we're not power limited. And then we couple it into the fiber. And then for the seed, we see the process on the signal side. It's a tunable 15XX ECA laser. And then we shape that into the seed mode. And then we also couple that into the fiber. These two together is going to generate an idler, which we then measure its spectrum. Now we sweep the seed wavelength, and then for each wavelength, we measure the idler spectrum, and that produces a two-dimensional spectral map for a photon pair that corresponds to the JSA. So if you do that for that process, this is an example of what we get. It is an anti-correlated JSA that features sidebands. This is for a 16 centimeter of a fiber length. But if we switch to a different process, say we pump at 18 and 19, which means a pump modal difference of 1, this guy is still anti-correlated, but the sidebands went away. So in order to understand why that is the case, it's best to view it in terms of what's happening in the time domain. So when you have a degenerate pump, meaning the two modes are the same, they'll have the same group index. And so when you launch them together in the fiber, they propagate together all the way at the end. So essentially, you have a very sharp onset and a very sharp offset of your nonlinear interaction in Z. And so in terms of phase, you get a sinc function, right, before you transform that. However, if you have a non-degenerate pump, right, then, meaning the two modes are different, then as you propagate through the fiber, because of their difference in group indices, they're going to experience temporal walk-off along the fiber, gradually deactivating the nonlinear interaction. And so because of this smoothing out of the interaction and phase domain, that gets rid of these sinc sidebands. Now, this is an example of one kind of engineering that we can do by changing the modes, but by changing to different processes, we can see that we can achieve uncorrelated JSAs, but also correlated JSAs. And so if you look at what determines the slopes of these JSAs, we find that it actually depends on the relationship between the group indices of all these four modes. And so this kind of leads us to one important conclusion, is that the effective indices between the four modes control where the process shows up, but the relationship between the group indices control how these processes look like. And this kind of makes sense because essentially the group index quantifies how much phase mismatch you accumulate as you deviate away from your central frequency. And so essentially it controls what's happening around the center and hence the shape. All right, so now that we know that we can engineer the spectral properties using, by changing the fiber modes, then we want to go ahead and actually perform some time-correlated single-photon measurements. This is in the spontaneous regime. And so we disable the seed. We only turn it on for alignment. So we pump the fiber again with the same mode, which produces our signal and idler fields. And then we pass these into their own MPLC setup to convert them back to Gaussian beams that are then coupled to single mode fibers and then detected by APDs. We specifically measure the temporal coincidence histograms as a function of pump powers. So for example, this is the histogram that we get for 1 milliwatt of pump power, and this is what we get for 30 milliwatts of pump power. And we can see that this guy features a strong coincidence peaks due to events emanating from the same pump pulse. And also it has accidental peaks due to events emanating from different pump pulses. And hence they show up at pump rep rates away. So essentially the ratio between them, the coincidence to accidental ratio or CAR, essentially quantifies how well you're preserving your pairs and also whether your source has any other contamination source like Raman scattering. So this is one metric that we care about in our source. Another thing that we care about is the heralded G2, which can be measured by splitting the idler into two and then measuring the threefold coincidences. Now, for an ideal source, when you're only emitting one pair at a time, you're never going to be able to detect like a threefold coincidence, and so this guy should be 0. In practice, it should be as small as possible. So this is what we got in terms of the coincidence count rates as a function of pump powers for both polarizations, as well as the single count rates as a function of pump power. In terms of CAR versus a function of pump power, this is what we get. We do see a characteristic 1/p² curve. And one thing that's notable over here is the fact that for the low pump power case, where we detect about 6.5 coincidences per second, we achieved a CAR of about 4,200, which to the best of our knowledge is the highest CAR measured for a fiber source using APDs. If we switch to state-of-the-art superconducting nanowire detectors, we can expect this CAR to actually go up. But this CAR also indicates that we're doing a pretty solid job at preserving our pairs, and also that we're not experiencing Raman contamination. And that is because the signal wavelength is far detuned from the Raman gain peak. You can get higher coincidence count rates, right? So we can go up to say 1 kilohertz over here, but of course that's going to be at the expense of CAR, which is still maintained to be at around 100 at this point. We measure, these are the results for the G2 measurements. And for the lowest pump power case over here, corresponding to about 75 hertz of detected coincidences and 1500 CAR, we measured a G2 of about 0.0045. What that means is that the probability of emitting two photon pairs is 6 orders of magnitude smaller than the probability of emitting a single photon pair. And so this essentially confirms that we're operating well within the single photon regime. All right. So I've shown you the single photon characterization for two processes of opposite polarizations, but of the same modal combination. Now we want to explore the highly multimodal nature of this fiber by characterizing and identifying many processes of different OEMs. So to do that, there are some few technical modifications that we've made. First, we switched to a larger core ring core fiber, a 60 micron fiber instead of a 30 micron fiber. And as you already know, the reason we do that is because we have more modes and therefore more processes. But the negative of that is the fact that we have weaker nonlinearities because of the larger effective areas. We also switched to a longer pump pulse duration, so 15 picoseconds instead of 150 femtoseconds. What this allows us to do is to mitigate walk-off effects, we'd say between the two pump modes. So we can probe processes with higher pump modal differences. But the negative of that is that we have lower peak power for the same average power, and we also have especially narrower JSAs because of the narrower pump bandwidth. We've also implemented a two-beam shaping setup over here at a pump, and what that allows us to do is to easily excite complex mode combs, OEM combs, and also to minimize coupling losses. And so with this modified setup, the objective then becomes to explore this fiber and identify as many frequency indistinguishable processes as possible that would serve as our high dimensional basis. So this is an example of a process that exists within this fiber. It corresponds to, with its JSA, this process corresponds to pumping the fiber at L equals -45 and -37 to produce a signal at -35 and an idler at -47. Sorry. The color scale. Oh, it's just linear from 0 to 1. Are you asking about the JSA? Yeah, okay, it's just linear from 0 to 1. Yeah, sorry. So so over here on the right-hand side, you can see its corresponding phase matching line and this net versus lambda profile. So in addition to this process, we have identified in total a total of 15 processes that emit OM correlated photon pairs at the same frequencies. And with each one is responsible to emitting a particular basis vector in our potential high dimensional space. And so, for example, if we want to generate a 15-dimensional state, then what we can do is we can activate all these processes at once by pumping all of their modes. Two things to note about these JSAs is one is we have artificially restricted ourselves to processes with pump modal differences of 8 and below. If you measure processes with 9 and above, you can potentially increase your dimensionality, but that is going to come at a particular cost, which I will detail later. Also, notice that all these processes except for one are non-degenerately pumped. Again, highly leveraging the two-photon destruction nature of forward mixing. So if you look at these JSAs, we can see that these top 3 exhibit more pronounced sidebands and are also negatively sloped, whereas the bottom 12 over here do not have pronounced sidebands and are positively sloped. So because of these categorical distinctions, we are going to refer to the bottom 12 as the class 1 processes, whereas the top 3 are going to be known as the class 2 processes. All right. So while we have identified each of these constituent processes that would emit their own unique OEM photon pair, we would like to confirm that they preserve high quantum single photon performance, just like before. So indeed, we measured the car versus pump powers or car versus coincidence counts for each of these 15 processes, and this is what we get. A few notable things about this is we managed to maintain a high car for all processes, about 4,000. We measured the G2 for process 13 to be about 0.0032, which is the degenerate process, 0.0016 for process 14, which is a non-degenerate process, which is all nice and good. But you can already start to see from this plot is that we're starting to hit a little bit of a pump power limitation. So many of these processes we're only able to probe just this low coincidence count rate data point. And also even for the stronger processes, we're able to only go up to say like 100 detected coincidences per second. So because now I'm talking about pump powers, here are the pump powers that we used in order to achieve these coincidence rates. And you can see that over here in the low coincidence rate regime from 10 to 20 hertz, we had to exert different levels of pump powers. So this essentially implies that we have some natural strength variations between these processes. So I guess the question is, okay, why do we have strength variations for all these 15 processes? And what are the implications for those strength variations? So to characterize the strengths, we can actually go back to the seeded case. So we can pump the fiber with 2 pump modes with powers AP and PQ. We can seed the process by introducing a seed with power PS, and together that's going to produce some idler power. Now this idler power is going to be proportional to the product of these 3. And so we can define the strength of a process by just computing the proportionality constant, which essentially tells you how much idler you're generating for a given pump and seed powers. So this is the expression for the non-degenerate case, but if you have a degenerate process, we have this extra factor of 4 to account for the degeneracy factor. So if you do that for all the 15 processes and you organize them based on their pump modal difference, this is what we get. The crosses represent the class 1 processes, whereas the circles represent the class 2 processes. And there are 2 notable trends that we observe over here. The first thing is that we notice a general decline in strength as you increase the pump modal difference. Also, we notice that these class 2 processes are stronger than class 1. So to understand why that is the case, it's most useful to go back to group indices to try to answer this question. So over here, what you're seeing is the group index difference between the two pump modes for all 15 processes. And previously in this talk, I've already told you one of the effects of having a group index difference, that the two pump modes are going to walk off from each other within the fiber, gradually deactivating the process, and therefore you can expect lower emission. And indeed, we notice that as you generally increase the pump modal difference, the group index increases accordingly. So that explains why there's a decline with pump modal difference, but that does not explain why class 2 is stronger than class 1. So to answer that question, we can look at the group index difference between the idler and the average group index of the pump. So essentially, this is quantifying how well the idler photons are keeping up with the average of the pumps. And we can see that for the class 2 processes, the group index difference is much lower, which essentially implies that for these processes, the idler photons are keeping up with the pumps a lot better than class 1. And so that explains why class 2 is stronger than class 1. We can do something similar to look at the difference between the signal group index and the average of the pump, and this is what we get. There's a little bit of a lower group index difference for class 2, but I wouldn't say it's too significant to warrant this difference. So essentially, this is all to say that when it comes to process strength, group indices matter again, right? Now, another factor that we have to consider when we're talking about differences in strengths is how well these four fields overlap with each other spatially, and how does that overlap change with process. So here, for example, on top of the index profile of the fiber, you see all the four fields, and they have a certain overlap with each other. But as you change the processes, because each mode is because of the shape, because of the fact that each mode has its shape relatively preserved, similar as you vary the mode order, you can expect that the total overlap integral is going to remain rather constant as you change processes. And we find that the relative standard deviation for this overlap integral is about 10%. So we wouldn't say that it's a significant driver of strength variations. Right. So while group indices matter for strength variations, that is not the case for the spatial overlap integrals. And this is actually one of the beneficial properties of our fiber modes, the fact that they don't really change size that very much, say like compared to other modal bases like the LP modes or the your Gaussian modes. All right, so now we understand why we have differences in strengths, but what are the implications of them? So say, for example, you want to activate all these different processes together by pumping the fiber with a uniform pump comb. If you do that because of the strength variations, your signal and idler amplitudes are going to vary. Now, this is a problem because then you would have to have some kind of post-selection filtering, which is lossy and also cumbersome to implement. Instead, if you take into account the strength variations by engineering your pump comb accordingly, you can pre-compensate for them by engineering your pump comb and to produce uniform signal and idler amplitudes. And so this would give you a post-selection free operation. Now, this is only pertinent to the case of when we want to activate multiple processes at a time, right? And so that is exactly the current step that this project is undergoing, which is going to be multi-process activation as well as entanglement certification, which is something that my colleague is currently pursuing. So what do I mean by that? So take, for example, two processes 1 and 2, with their corresponding pump modes. We can construct a pump comb that contains all four modes. And if we pump the fiber with this comb, we can ideally expect this two-dimensionally entangled state with these correlated OEMs for the signal and idler fields. We can pass them through mode analyzers, which I'll explain how we do that, and we can then measure the coincidences. So this is very similar to how you would say, for example, certify polarization entanglement by passing your states through polarizers or wave plates to analyze the polarization. So this is the spatial mode analog of that. And we can implement those analyzers also using MPOC, right? So this is, for example, an incoming signal field that's a superposition of -35 and -36. So it has this crescent moon shape. And you can compute using MPOC the phase masks to convert a superposition of two modes to a Gaussian beam, right? And you can vary the phase between these two modes, and you can see that what it does essentially, it just rotates the interference pattern, and in turn that causes a rotation in your phase masks, right? So if you pass that through this analyzer and you vary the phase, then you get your characteristic sinusoidal behavior that is very similar and analogous to polarization, right? And so essentially that means that we can do entanglement certification using MPOC. We have obtained some promising initial results, but currently they're undergoing verification and optimization. So hopefully you'll get to hear more about that in the future from my colleague. So that's what's happening right now, currently as we speak in the lab. But potentially we can also look at other fiber structures to say like optimize for different things. So I've shown you some results for a 60 micron core size. But we also have another iteration of these ring core fibers that is that its size is 86 micron size. And as you would imagine, by going to a larger fiber, it becomes a lot more multimoded, and so essentially you have even more modes to play with. The group indices is also a lot denser, and now we have learned that group indices matter a lot and the system, right? So you can access more group indices, and that gives you a lot more controllability. However, of course, again, by switching to yet even a larger fiber, we're going to get even weaker nonlinearities. So that could be a potential bottleneck by going to this route. We can potentially explore other routes in the future, such as going to a small core, so like a smaller core size, but have an air-clad fiber that essentially exacerbates your index contrast so that you have a small core, which is good for effective area. But the large index contrast means that we preserve the multimodal nature of the fiber. So this could be a potential avenue to go to. And then finally, down the road, right, in the future, we actually hope to see this source integrated in some kind of like a quantum network system. Say we will, you produce our photon pairs, our qubits, and then we ship one to Alice and then one to Bob using a long OEM fiber, right? Quantum OEM transport has been done before with a smaller ring core fiber. So we hope to demonstrate something similar in the future. And you can even do some more fancy stuff like using ever-evolving space division multiplexing techniques to separate out the modes and have them interact with different physical systems to sort of entangle multiple systems far away. So with that, what are the main takeaways that I hope that I have conveyed in this presentation? First is we have these ring core fibers and their constituent OEM modes. These fibers allow for stable guidance of OEM modes, which allows us to actually use them for nonlinear optics. These OEM modes exhibit topological confinement, which allows us to push the number of modes. We can perform arbitrary beam sculpting using the MPOC technique, which gives us a versatile control for the transverse amplitude and phase. And that is very applicable to, say, engineering different pump OEM combs, or maybe even analyze your produced signal in either photons. We have done some single photon characterization, and the OEM correlations is due to the OEM conservation of this process. And we have shown that we can tune the properties of the joint spectral amplitudes by choosing different modes. And the location of these processes is dictated by the effective indices. The shape of these processes is dictated by the group indices. We also measured high CARs of about 4,000, which confirms good photon pair preservation and also a lack of contamination from Raman scattering, and also low heralded G2, which confirms that we're operating in the single photon regime. We've expanded that into a high dimensional system by exploring different modal combinations. And this is allowed by, this is enabled by the fact that we have a higher effective index density, which gives us a lot more processes to explore. We have identified to date 15 spectrally overlapping processes, which would serve as a basis to realize a 15-dimensional quantum state or quantum space. They likewise maintained a high CAR and low G2. And also we learned that their process strength variations are largely driven by the relationship between the group indices. And from here, we're actually currently pursuing multi-process activation. And also, we may go to future fiber designs and hopefully full integration with a quantum network. So with that, I'd like to give my acknowledgments. First and foremost, my advisor, Professor Siddharth Ramachandran. Again, thank you for taking me in to his lab. It's been a pleasure to work with him in the past 5 years. I learned a lot from him. I would like to thank Dr. Paul Christensen from Litera, formerly OFS Denmark. He is the guy who manufactured our fibers, and so without him, these experiments would have not been possible. I'd like to thank our collaborators, specifically Professor Virginia Lawrence from UIUC, who kind of like helped us a lot with the quantum measurement aspects. I'd like to thank past lab mates for their invaluable mentorship. And I would also like to thank present lab mates, with a specific shout out to Sanjana over here. She has been working with me on this project for the past couple of years, and she's going to be the one to pick up the mantle, once I leave. I'd like to thank my friends and family. Special shout out to my wife, Mickey. She had to put up with all my crap over the past 5 years. I'd like to thank our funding agencies. And finally, I would like to thank you for your attention.
I was really interested in the idea of changing the intensity of your input signal to sculpt sort of the equivalent power up on the output side.
Yep.
But it occurred to me that are those all non-degenerate processes on the input? Are there multiple input intensity profiles that can give you equivalent output profiles?
I don't think so. I mean, because all the pump modes are rather unique for all these 15 processes. It's not strictly true. I think there's 15 processes. So if all the pump modes are non-unique, then you would have 30 pump modes. But some of them do have some overlap. And so, taking the extreme case that they're unique, then that means there shouldn't be any two equivalent pump combs that would give you the same distribution of the output.
So the takeaway I got was the importance of group index, especially for nonlinear interactions for optimizing in your case, I guess, Chi2 or spontaneous downconversion process. Was the dispersion of your fibers particularly engineered because you had like two very different wavelengths to go across the entire fiber to get that phase matching preserved to generate that nonlinearity? I just wanted to know, like, I think standard Q silica, just the dispersion might be alone from like 780 to what 1 micron would be too far away. Like some special material, like I've done stuff nonlinearities in BBO. Like you want to compensate the femtosecond pulses, the walk off in BBO, 50 micron or 100 micron. You need to introduce some kind of birefringent material, like I use calcite to compensate for that spatial walk off.
Right. Yeah, so I mean, you're right that in many of these fiber systems and nonlinear optics, a lot of them are dispersion engineered to specifically target different wavelengths or different properties of your output modes. In our case, we are not doing anything special in terms of dispersion engineering, so like putting in trenches and all that. All we're doing is actually leveraging the fact that we have modal dispersion in our fibers. So our dispersion engineering, quote unquote, is the fact that we have all these different effective indices and dispersion properties for different modes, right? So the dispersion engineering comes inherently within this plot over here, right? Did that answer the question?
So they can jump different modes.
Yeah, you can just match, right? I mean, the only thing that matters is to phase match the 4 photons, which geometrically is just forming a line over here. Now, of course, you cannot draw any line because it also needs to satisfy OAM conservation and also energy conservation, right? But this is the modal dispersion advantage that we're that we're using.
First of all, cool that you can use multi-modes and higher order modes for a real positive way. I don't know how often that is done, actually. But secondly, to question on your results, I was just curious, there was that slide. What's the difference between the two different classes? Was it the side mode?
Yeah, so I can go back to
On that slide, I couldn't see the difference, but
yeah. So the this is the first slide that I introduced that. This is that. The slide before it. Yeah. Okay. Oop. Sorry. Yep.
Yes, how do you tell that it's broke?
Yeah, so you can see that these guys, you know, you can see like a more pronounced sideband over here, right, compared to the main lobe, whereas this guy doesn't have sidebands. Oh, sorry, my bad. Right, so for these top three, right, you can see these a bit more prominent sidebands, compared to the bottom 12 over here.
Okay, so it's
Yeah.
that extra.
Yeah, it's not extra green, and there's nothing really fundamental between these two groups of processes. It's just some categorical distinctions that we notice. It's like, hey, these modes are such that, you know, their group indices show up in such a way that this is how the JSA looks like versus these bottom 12. You can also notice that they're also different in terms of like the slope of that forward mixing line. So, but there isn't really anything like fundamentally different between the two. It's just some distinctions that we noticed. But these distinctions kind of carry over to other things like the differences between the strengths. Like we noticed that just by by the way that these modes are, that these processes are stronger than these processes, right? Just based on the mode selection itself.
What's your tolerance in terms of overlap between JSAs to say that two processes would be indistinguishable? For instance, like 2 and 14.
Yeah. Yeah, I mean, you're bringing up a good point, right? So these JSAs show have some frequency overlap in the 799.3 and also 1564.8. But yes, the overlap is not 100% perfect. Definitely you can see some very slight deviations. Those deviations can be corrected for by, say, like broadening your pump holes to facilitate like a better overlap, because if you broaden the pump, you also broaden the JSAs, and so that actually kind of makes it easier to have a better overlap. So yes, you're right. Strictly speaking, while these do show spectral overlap, it's not perfect, but we hope to improve that in the future.